Hello, I'm Mary Hall, and I'm a professor in the School of Computing at University of Utah. And this is Virtual HPDC 20. You may have heard repeatedly by now that data movement is the most critical optimization goal as we move to exascale architectures. Today's talk, entitled High Performance is All About Minimizing Data Movement, we'll look at optimizing data movement from a software perspective. First, I'd like to acknowledge my collaborators on this work, particularly my PhD student, Tuowen Zhao, and Lawrence Berkeley Lab collaborators, Sam Williams and Hans Johansson. This research was sponsored in part by the Department of Energy Exascale Computing Project and also the National Science Foundation. It used resources from the Department of Energy labs to produce the experimental results. I'll start by providing context for moving software to current and upcoming systems. This is perhaps a familiar graph from Kogi and Schauf. It's showing the energy required for different operations and moving for floating point operations and moving data across a chip and across a system. And note that it's a log scale, and the blue line refers to modeling of 2008 systems, and the red 2018. And keep in mind this was done in 2013. It shows that the energy costs in a 2018 system of floating point operation is exceeded by moving its operands just 2 millimeters across a silicon chip. It also grows significantly, see that it's a log scale, as we move farther, as we move data farther and farther in the system. This graph's been used to argue that the true cost of future system in terms of energy, dollars, and performance is data movement. So computer architects have thought a lot about both scalability and optimizing data movement to design the exascale and near exascale architectures that will soon become available. To get a preview of these, we can start with the top machines from the top 500 list of current supercomputers. These 4 systems all have different processing technology. We have NVIDIA GPUs, both the P100 and V100 generation. We have a custom processor in the Sunway, and Intel Xeon Phis and Tiani 2. These processors, these systems all have specialized, highly parallel processors, which are often combined with general purpose CPUs. These processors support a variety of programming models, including standards like MPI and OpenMP, as well as OpenACC, CUDA, and others. This current environment, with a diversity of architectures and programming models to support them, has created a performance portability challenge. How can we achieve high performance across platforms without a fundamental rewrite of our codes? And now, if we look at what's next, these are announced systems with even more architectural diversity. We have new offerings from AMD, Intel, and ARM. And now we have even more programming models, including HIP and SYCL. So how do we unify software development across these architectures so that programmers have a way to develop performance portable code? Our solution is for data movement to drive the programming system. While hardware specialization has gained popularity, software specialization has similarly been used to improve both programmer productivity and performance. So domain-specific systems are that specialization. They customize optimization for a specific application domain. It's a lot easier to do this than building a general purpose compiler, for example, or new programming language, because you can encapsulate just the main core primitives of that domain in your system, and allow programmers to specify their application in a much more productive way. Much less code is required. And if there are multiple target architectures for the system, then it can achieve both high performance and performance portability. There are tons of examples of domain-specific frameworks across a variety of domains, and I just listed a few here. Since we're going to talk a lot about stencils, I put more stencil examples in the list, but I also show sparse linear algebra, tensor contraction, big data, and deep learning, and many, many other domains. So this idea has gotten a lot of traction, particularly recently, even though some of these things go back decades. The idea is to build a domain-specific programming system around the notion of packed data layout, which is a collection of many subdomains, each representing the smallest unit of aggregate data and parallel work. So the data layout for a node is a collection of these units. And we have a flexible organization in this layout, and in that we can both reorder the data and aggregate the data in different ways for different architectures. And we can even change the size and shape of this unit of data. And so this flexibility provides performance portability. The result is that we can speed up the data movement that's required. We can reduce the need for the data movement. And finally, we can reduce on-node data movement that's required for communication, which will improve strong scaling. So these are the claims of the work that I'm going to present today. And I will spend the rest of the talk showing you how we meet these claims, and also generalizing to the approach to look at other application domains. But let's first take a brief detour to clarify the types of data movement this work addresses. To program the earliest cluster-based supercomputers, the primary concern was data movement horizontally across a network from one node's global memory to another's. The thinking was that processors were getting faster following Moore's law, and so we designed programming systems that tried to minimize both the amount of communication and, more importantly, its frequency. So we call this horizontal data movement. An example of horizontal data movement is communicating data between two nodes across the interconnect. Within a node, the memory wall soon reared its head, the result of the performance divergence of processing and memory speed. This raised concerns about moving data vertically through the memory hierarchy. So let's drill down a little bit on this expanded picture of a node. We have processing logic and a cache, a private cache for that processor, or maybe a cache hierarchy. And both processors share a global memory. There's also a memory management unit, which in this case is also shared by both processors. And now if we go a little bit deeper into the processor logic, we see that it has minimally an ALU and a set of registers. So examples of vertical data movement are from global memory into cache and from cache into registers. And keep in mind, on modern architectures, these registers may be vector registers of very, very wide vector registers. And here's another kind of data movement, vertical data movement, that you might not be thinking about, but turns out to be really important. During program execution, processors use virtual addresses that must be translated to physical addresses by the memory management unit. So here's a memory management unit blown up into more detail. And virtual addresses come in and physical addresses go out, and the cache is indexed by, the data in the cache is indexed by its physical address. The memory management unit contains a small cache of the virtual to physical mappings called a translation look-aside buffer, or TLB. So another form of data movement, of vertical data movement, arises when TLB capacity is exceeded. And this translation needs to consult the page table for this process, perhaps located in global memory, as in this case. And now with GPUs and other accelerators, which tend to be subordinate to general purpose CPUs, another kind of vertical data movement is between CPU and accelerator memories. And I've drawn it kind of diagonal, but the accelerator is part of the node, and so this is part of vertical data movement. To communicate data from one GPU to another requires horizontal data movement, often passing through the host. And there are APIs that do, in some cases, allow you to bypass the host when you need to do GPU to GPU communication. So we're calling this vertical plus horizontal data movement. It's vertical if the CPU is involved. We need to think holistically about how the programming system can unify optimization of data movement to achieve performance portability using the concept of packed data layouts. So now we discussed how this idea can be used to optimize stencil computations. Stencil computations arise in solving partial differential equations. The outputs are computed from neighbors in a multi-dimensional space, and they're multiplied by a coefficient. This access pattern arises in convolutions too, which are part of deep learning systems. So in these pictures on the right, these are common stencil shapes in 3 dimensions. And the different colors reflect the same coefficient being multiplied by points, different points. So the number of inputs to a stencil is related to its order. So low order stencils, which have few inputs, are memory bound because you must read the data in. It's not reused very much in the memory hierarchy, and there's very little computation going on. When you do a high order stencil, such as this 125 point stencil, in this picture, there's a tremendous amount of computation going on, and there's a tremendous amount of reuse of data. So these tend to be compute intensive, but they also have data movement issues because there's a very large volume of data, and you may have a lot of trouble retaining that data and even the register file long enough to do the operation. So So let's make the data movement in stencils more concrete with an example of a 13-point stencil. So this is a two-dimensional star-shaped stencil. These 12 points, the blue inputs, form a star in 2 dimensions. And here's a corresponding code that is applied to points in the input space to compute an output. There's vertical data movement, since stencil inputs can come from a large number of address streams. If the output determines domain decomposition across iterations, remote data is needed for inputs, and the storage reserved for remote data is the ghost zone. There's horizontal data movement to communicate the ghost zones, and you may need to pack that data into messages. Let's look at this 13-point stencil in a little bit more detail. So just to compute one output point, we need 7 different address streams for where the 12 inputs reside. So these 7 address streams correspond to 7 different cache lines, for sure, and may even correspond to multiple pages. And so having a lot of address streams puts pressure both on the cache and on the TLB. And you can see that we're not utilizing all of a cache line. If this adjacent data corresponds to a cache line, we're only accessing one element in it. It's also going to limit hardware prefetching, because a lot of address streams means that the hardware prefetcher is trying to optimize a lot of different things, and we'll have to make some tough choices. We're going to have alignment issues associated with vector registers, and as we perform the computation, we're going to need to reorder the data in registers. And now let's think about what happens when we do something that is commonly done, when we add something that's commonly done to reduce the footprint of data in cache. That's tiling. Tiling is going to introduce even more address streams, particularly if we make the tiles relatively small. And parallelism, thread level parallelism, is going to add even more address streams. So as we increase the core count, or we increase the amount of parallelism, we're going to put more pressure on the system. This slide looks at horizontal data movement arising from stencils. Here on the left, you can see the blue area is a surface of the stencil domain that's assigned to a node. And we've numbered them so that we can talk about them here with the messages that we want to send. So this node has 8 neighbors in 2-dimensional space. It has the neighbor to the north, to the south, to the west, to the east, and then it has these diagonal neighbors. So when we want to send data, for example, to our western neighbor, this block 1, 4, and 6 are not contiguous in memory. And so typically they would be copied into some kind of buffer before performing the communication. So over here on the right is the communication we want to perform. We want block 6, 7, 8 to go north, 1, 2, 3 to go south, etc. And these are going to our diagonal neighbors. So it's common to pack this data before sending it on the interconnect. But the time that you spend doing that packing can be significant, and sometimes as costly as sending the data on the interconnect. So it limits strong scaling because the cost of doing that packing contributes to the communication costs. Now let's look at how we can use a packed data layout to reduce data movement costs and achieve performance portability for stencils. And for this purpose, we built a brick library, which I'll describe across the next couple of slides. The unit of work in data is called a brick. A brick is a mini subdomain, for example, 8 by 8 by 8. And it doesn't have a go zone because it's small, and we would be wasting an enormous amount of storage if we supported go zones. But consequently, application of a stencil reaches into other bricks. And that means that affinity is important. What bricks are being executed by a thread ideally should be neighbors of each other. Maintaining this layout is implemented by having individual bricks be contiguous in memory, but the neighbors we keep track of through adjacency lists. So we said this earlier, we have a logical ordering that's captured with adjacency lists, and the physical ordering could be something different. The next couple of slides are designed to make the discussion of the brick layout a bit more concrete, so they peek into the library implementation. So you can express your stencil in Python. And in this example, we have brick input and output arrays in and out, which we declared at the top. And out we have references to out and in that look like two-dimensional references plus a brick index. Sometimes you're going to go outside of the brick. For example, if you're on the edge and you say +1, and these accesses are going to be resolved automatically by the underlying system. So you end up going to a different brick instead of going off the end of your own. The library includes a vector code generator that builds a directed acyclic graph looking for opportunities to reuse vector data and operation, partially computed results. And it looks across grids in order to identify this reuse. So here's some examples. We have these blue nodes are marked as reusing data because you can see they're accessing cons I and y in both cases and multiplying it by del and gam. And here we have reuse of this cons IMX across del and gam. But there's an interesting thing going on here. You can go and look at the code itself, and the access that's multiplied by gam is +3 -3, and del is +4 -4. So there is reuse there, but the vector has to be shifted in order to exploit that reuse. And that's an aspect of the vector code generator, is identifying those opportunities and exploiting them, creating buffers for shared data and exploiting the reuse. In order to take advantage of that reuse, it needs to reorder the computation. So it uses associative reordering, which is also a common technique in stencil computations to be able to exploit that reuse, even in this case across these different stencils. And the brick size can be adapted to register pressure of the stencil as well as the architecture. So this particular example, we're going to come back to it in the results, needs a smaller brick size because of all the different grids that are simultaneously being computed and sharing some of the same input values. We can aggregate a collection of bricks together to execute on a node or to be executed within the same thread. And we use indirection to allow a different physical layout from the logical organization. So brick storage is where we actually store the brick data, and it is numbered with an index corresponding to its physical location. We can reflect a different logical layout with brick info, which is basically keeping an adjacency list for all the nodes. And is that reordering the difference between the physical layout and the logical organization that allows us to perform the communication optimization and take data that needs to be communicated to a neighbor in the network, make it contiguous in memory. So in the picture on the left, a node surface has to be communicated to the ghost zone regions for all the neighbors in its 2D space. According to the color coding, we have laid out the data and so that if it needs to be communicated to the same neighbor, it's adjacent in memory. So the numbers in the middle figure reflect the physical organization of the data. For example, what their index would be in brick storage from the previous slide. By optimizing the physical layout for communication, the communication is pack-free. So the bottom of the slide shows some of the brick library functions that support this data layout and ghost zone exchange. Declaring the domain, selecting a predefined layout, and allocating the input storage, and then for each iteration of the time step, there's a ghost zone exchange using a special library function that knows how to exchange data based on this layout. Okay, so now we can show experimental results and find out, do bricks really reduce data movement? So the first are from single node results. This graph shows the performance gain for brick implementation for a variety of proxy stencils and targeting 2 CPU architectures and a GPU architecture. So Intel Xeon Gold Skylake X and Intel Xeon Phi KNL. And the GPU is an NVIDIA P100. We compare 3 versions of the code. The baseline is a highly optimized multi-dimensional tile code, parallelized and vectorized with OpenMP and using the same strategy as the other versions of the code. The third version, labeled brick, uses the brick data layout and it uses the vector code generation that I previously described. One in the middle, labeled tile, is a tile version, but with the same code generator as the brick code generator. So the brick version consistently outperforms just tiling and achieves speed up across all the architectures over the baseline. And achieves speed up on everything for the P100, and it tends to achieve the most significant speed ups across the board for stencils that are high order and have lots of input data. We use performance monitoring to probe the performance differences more deeply on a multi-stencil computation from Hypterm that you saw in a previous slide. The results shown here for the KNL and for the P100. And we see that bricks really do reduce data movement. On the KNL, this is primarily due to huge reductions in L2 misses and TLB misses. You can see this as a log scale, and those differences are significant. On the P100, the performance gains are due to a reduction in loads due to improved register reuse. Okay, so now we can look at the communication results. This is for a 7.3D stencil and is showing the benefits of pack-free communication using bricks and a layout optimized for communication. On the left, there's the KNL. And this in the graph on the right, the x-axis is the size of the subdomain per node running on a system with 8 nodes. As we move to the right, the subdomain gets smaller, which is a proxy for a strong scaling experiment. The curve labeled network shows just the network time. Layout performs the ghost zone exchange and is only slightly more costly than bared network time. The other curve labeled YASK is a state-of-the-art adaptive stencil framework for KNL. It performs packing and is substantially slower for the small subdomain sizes, but performs pretty well for the larger one. Using MPI types, which is a common approach to optimizing this packing, will still internally pack messages, and it results in the worst performance overall. So on the right are results for the V100, and we're evaluating 2 versions that use the layout optimization. One uses CUDA aware with GPU direct, while the other uses unified memory. The CUDA aware version is very close to network time and significantly outperforms the MPI types version. Here's a number of observations from our experiments that really didn't show up in the results directly, but were quite interesting. First of all, smaller brick sizes, for example, 4x4x4, sometimes improve performance as compared to 8x8x8 for multi-stencils and high order. And the reason for this is that they use less storage. Once you have a lot of stencils, they're competing for the same resources. And so it's beneficial to reduce the footprint of the stencils so that you can get them to fit in registers and cache. If you have a vector width that's bigger than the contiguous dimension of your brick, then you can use a technique called vector folding to create sufficiently wide vectors. So what you're doing is taking 2 of the dimensions and folding them to be one-dimensional vector and performing the calculation on that. A couple of interesting things in the GPU code generation. First of all, non-square bricks were used on the GPU, and warp shuffle was used to exploit reuse in registers across threads. On the communication optimization side, we were curious as to whether a physical data layout designed to optimize communication would cause us to lose the memory hierarchy performance gains. And we verified that there's no appreciable difference if you lay out the data in corresponding to the logical order in which it's accessed versus the order needed for communication. The second thing I haven't really mentioned is communication avoiding, which is making the ghost zones larger than the stencil radius in order to trade off redundant computation with communication and reduce the number of times, the frequency in which you need to exchange ghost zones. So if you have a brick that that holds the ghost zone, then say you just need one element per iteration, then it's 8 iterations between exchange for an 8 by 8 by 8 brick. And note that the same approach that we use here was shown to be useful when communicating between subdomains on the same node. Finally, that this communication approach, even though we're talking about structured data that we're using for the stencil examples, the same communication approach generalizes to AMR, to adaptive meshes, due to the fact that the framework is built around the notion of indirection. Okay, so we've talked a lot about stencils, and maybe your application is not a stencil, but you still have a lot of data movement in your computation. So how do we generalize this approach to other domains and achieve the same performance benefit? So there are a few research groups that have used packed data layout, and in some cases for other applications. And so the question is, can we generalize what we did for stencils? So first of all, this data layout should be a configurable unit of work for an architecture and also for the application. And it needs to be the appropriate size for data movement and also for parallelism and parallelism aggregation. Then you need to build a software layer for organizing and parallelizing a collection of such units and performing architecture-specific code generation. And if you want to support applications that were written outside the library, then you need to be able to convert from standard data layouts automatically. So I want to take a little bit of a deeper look at generalizing this approach to sparse tensors. So I use the phrase sparse tensors, but a lot of the research in this area has been done on sparse matrix computations. In a sparse matrix, you only want to store the values of the matrix that are non-zero. And you need an auxiliary set of representations to be able to reconstruct the row and column corresponding to each sparse element. So the literature includes a lot of different matrix representations and both libraries and compilers that perform this transformation from one matrix representation to another. If you're looking at sparse tensor computations, the data may be accessed in multiple modes during the same computation. And that a mode refers to which dimension is leading or the order in which you access the dimension. So there are techniques, there are matrix representations that are designed to be able to optimize for given mode or in general for all modes. And so I'm pointing to this one paper from SC18 on a representation called Haiku, which I think is very closely related to what we've been talking about in this talk. I also, in the abstract, referenced previous work from my own student, Anand Venkat, on automatic code generation to transform sparse matrices from one format to another. And I do want to make the connection that There is a packed data layout that has been used for dense tensors. It's named according to the order in which the dimensions are traversed and are laid out and split. And now I'd like to talk a little bit about related work and summarize the talk and discuss what we plan to do for the future. So there has been a lot of research on stencils over a long period of time. So just going to point to a few things. Most of the research is focused on stencil memory hierarchy optimizations. And that goes quite a ways back. And some of the work is about stencil communication optimization. So in particular, the stencil communication optimization has focused on overlapping communication and computation and communication avoiding optimization. And there's been recent work on MPI derived types to describe strided ghost zones to address the kinds of issues that we talked about today. And moving to the right, there are also recent work on stencil vector and register optimization, really trying to get performance out of the code that's generated. So vector folding, I mentioned earlier, is part of YASC. Associative reordering, I also mentioned earlier. GPU register optimization, which identifies reuse from a DAG. And data layout transformation, which deals with alignment issues in stencils as you move across the dimension. I want to end this side by talking about packed data layouts. Briquettes is a similar idea, also applied to stencils, but not including many of the optimizations that we discussed, not worrying about vector code generation, not moving the layout around for communication. There have been techniques for sparse tensors and sparse matrices. I mentioned haiku, but there's also some work for 2018 on dense storage of sparse block matrices. And then recently, for relativity calculations, framework has been developed to improve communication by using packed data layouts. So I'm going to close with a summary and the work we plan to build on what I described today. So what we showed in this talk is that packed data layouts achieve performance portability and reduce vertical and horizontal data movement. So we have a bunch of ongoing work. First of all, to deploy the brick layout in an application framework for stencils, and to demonstrate the generality of the approach for sparse matrix and other domains. In the future, I like to build compilers, and so I'd like to take some of the technology we've developed in the brick library and instead develop a layout-aware compiler integration for domain-specific optimization. So it's possible if you have a domain-specific problem that is heavily dependent on the data layout, that this layer of optimization would enable you as a compiler developer to be able to perform those optimizations in a context of a compiler. And then finally, when the exascale platforms emerge, we want to demonstrate performance portability for these very different architectures. That concludes my talk today. I want to thank the organizers for giving me this opportunity to give this talk. And I want to thank you, the audience, for listening to it. If you are watching this before the main HPDC conference, I will be available on Thursday to answer questions during the Q&A session. Hope you all enjoy Virtual HPDC 20. Thank you.